All right, so again, this is our last panel of the day. And we have a tremendous luncheon and some people to speak. Let me find my end of my script. So Northrop Grumman and Teledyne Brown, thank you very much for sponsoring today. We appreciate it. And now we will just go straight into it with our moderator, Nikki Fox, Heliophysics Division Director, Science Mission Directorate, NASA Headquarters. Thank you, Nikki.
Thank you so much. It's a pleasure to be here, and I realize we're standing between you and lunch, so we will try and keep this really exciting and interesting for you. I think there's a lot to build on from the last panel that we heard. There's a lot of similarity between the type of work and actually the real partnerships between NASA and NOAA, and then the real support that we get from our industry partners. And so I think there's a lot of parallels we can draw. I'm delighted to be joined by this very wonderful panel. And I'll give them real quick introductions, and then I'm going to, you'll hear some great stuff from each of them. So Ginny Meehan is with us. She is the National Space Weather Program Manager at the National Weather Service, and a real expert in space weather, and also helping us with all of our interagency panels. She's a very, very, very busy person right now. And so she's going to be giving you a lot of the NOAA perspective. Also joined by George Ho, who is a chief scientist at Johns Hopkins University APL, and he recently led a team that completed a gap analysis, like a space weather gap analysis for us in the Heliophysics division, and I'm sure he's going to be talking a lot about those gaps. And then Jari Collado-Vega is the director of the Moon to Mars Space Weather Analysis Office at NASA's Goddard Space Flight Center, and she is an expert in all things space weather, particularly how to track those events that we see on the solar surface and predict what they are going to do all the way down to the Earth's surface. So she's going to tell you a lot about that. And then last but certainly not least, only last because he's furthest away from me, Paul Galloway, who is a senior systems engineer at Teledyne Brown. And he's really going to talk to us about the technology and the technology advancements necessary to be able to really improve our ability to do space weather. And so I'm going to close my eyes and hope this works. There we go. Yay. So I was going to start off by telling you, in case you hadn't noticed, Solar Cycle 25 is here. The sun is waking up. We had a very, very quiet solar minimum. In fact, there was even a period where we had no sunspots on the sun. But beginning December 2019, we marked the beginning of the new solar cycle, and we're seeing the sun's activity once again ramping up until we get to solar maximum, which is predicted for 2025. Now, of course, we anticipate this new solar cycle seeing an increase in space weather events. And of course, that will impact our lives and our technology on Earth and our astronauts in space. And as we gear up to do more crewed missions, and we are ready to support the Artemis mission as we return astronauts to the moon and then hopefully onto Mars, it becomes even more critical that we understand our environment. Moreover, this is really the first solar cycle that many of our new commercial and government stakeholders will navigate, i.e. be in orbit. And you can see at the very top there on the right-hand side, February of this year, we did see actually a very moderate space weather event. It was nothing that any of us got excited about, to be honest. It was actually quite slow. The flare and the event happened on the 30th of January, and it didn't actually really get to Earth till February 4th, which is a pretty slow event. We get excited about things that come in 2 to 3 days. This was a very slow event, but it caused geomagnetic conditions that actually affected the launch or the on-orbit operations of 40 of the newly launched Starlink spacecraft. So for sure, we are excited about doing the space weather, doing the science, particularly at NASA, doing the science that will enable better predictions. I'm just going to flag, I threw it in there for a bit of fun for Parker Solar Probe fans. The movie that you're looking at the bottom, that is from the last perihelion pass. And if you cannot see how active that sun is, really close up, excuse me, you can see just how many solar events are coming off that sun. So I just thought I'd throw that in for a bit of fun. Fun is a whole different definition to me. So I thought I'd just also take a moment before I pass along just to tell you kind of what we're doing in the Heliophysics division towards ProSwift. And we are really excited at NASA about what ProSwift has given to us. Because it really allows NASA to focus on what we do best, and particularly what we do best in space weather. And that really is pushing the boundaries, really pushing what we understand in the Sun-Earth system. And then, how that then leads to an evolution of our space-based network. One of the questions I'm going to be asking the panel is what do we do next? How do we fill the gaps? What are the most important things that we don't have currently in our arsenal? But it really allows us to focus on the science and then working with our partners, particularly in NOAA and with the DoD. How do we transition that into actionable, usable data for our stakeholders? And so with that, I will happily pass on to Ginny. Oh, you've got your own. Yeah.
Is it on? Okay, sorry for the, it's slowly coming on. Okay, so it's my life right now. Okay, so I'm Jenny Meehan. So I am the National Space Weather Program Manager for the National Weather Service, as Nikki pointed out. I'm also the designated federal officer for the new Space Weather Advisory Group and the executive secretary for the White House Space Weather Operations Research and Mitigation Subcommittee. In other words, I never sleep. No kidding. I have a 6-year-old and a 2.5-year-old, and I don't sleep really. Okay, anyway, so I'm going to spend just a few minutes providing just a broad overview of recent national policy initiatives, as well as an update on what NOAA is doing to support these policy initiatives. So as you just heard from Nikki, the sun is waking up. Solar cycle 25 is here, and it is definitely making itself well known already. And so the need for space weather products and services has evolved substantially over the past decade. And so in order to keep our nation prepared and safe, a number of national policy initiatives have been developed to advance space weather research, observations, modeling, and our operational capability. So how are we becoming a space weather ready nation? Well, the core elements of our national priorities are to mitigate the effects of and build resilience to space weather storms. And we're doing this by, we have to advance our understanding of space weather phenomena. So not just do we need to understand our sun, but we also need to understand the heliosphere and our near Earth environment and the very complex interconnected layers of atmosphere into space. We also need to have in place an operationally dedicated space weather observations, both ground-based and space-based. And then we need to transition all this incredible research that NASA is doing, that other federal agencies are doing, our academic partners are doing, our national labs are doing, and our commercial sectors are doing, both in observations and in models, and incorporate that into operations at NOAA and also at the 557th Weather Wing, which is dedicated to providing space weather alerts and warnings to the national security sector, apart from NOAA's mission. So this is a ginormous undertaking, what you can imagine. This requires an entire community approach, both with the federal government and also with our public and private partnerships. And so there is so much to be done, so much to be done. Space weather covers a vast, huge domain. And so we're doing something about it. Right. So we have statutory and policy frameworks provided by the ProSwift Act, which Nikki mentioned, also by the National Space Weather Strategy and Action Plan, and also some executive orders the previous two administrations have signed. And one very important one that President Obama signed about 6 years ago was it formalized the White House Space Weather Operations Research and Mitigation Task Force into a subcommittee. And that unites the national and homeland security enterprise with the science and technology and operations enterprise. And so then the previous administration codified the SWIRM into law with the ProSwift Act. So there are over 34 different federal agencies, departments, and offices that are a part of the SWIRM. And this group is tasked with releasing a national strategy, space weather strategy and action plan that identifies those strategic objectives and high-level action necessary to achieve a space weather ready nation. And what it does is it also leverages existing national efforts and seeks to align the federal government efficiency and also enhance American innovation. And so this document is actually due for an update, and we kicked off that process at the previous SWRM meeting in February. So things that the SWRM will prioritize are space weather R to O to R, updating the space weather benchmarks, updating the space weather scales issued by NOAA, and is how NOAA issues their alerts, forecasts, and warnings. And then also a huge priority is hazard mapping, which is very hard to do in space weather, okay, because we just know that space weather is coming towards the Earth, okay, at this point. So hazard mapping is very important. And then observations and modeling necessary, not only to enhance what we are predicting now, but also to support human spaceflight and space traffic coordination and space situational awareness, and also aviation. And then also we need to ensure plans are in place for response and recovery to space weather events in all sectors and with our stakeholders. And then critical to understanding or critical to predicting and forecasting space weather is our ability to observe space weather. And so we need to ensure that we have continuity in our satellite missions on that sun-earth line, and then also seek novel space-based observations to further enhance our ability to forecast. And so the ProSwift Act is also another very important piece of legislation that will help us become a space weather ready nation. So I just spoke a little bit about what the SWRM is doing to advance our nation, but the SWRM is just federal departments and agencies, right? And so the ProSwift Act actually did something incredible. It directed NOAA to establish a new space weather advisory group that advises the SWRM. Okay, and so that advisory group is all non-government. So it's 15 members, 5 from academia, 5 from the commercial space sector, and then 5 from end users. And so one very important task that this advisory group will do as we're standing up, we just stood up, we established this advisory group last year and have since had 2 meetings, one recently last week, right? Yeah. George is on the advisory group, so thank you for your service. Okay. Oh, yeah. George is like, why does she keep emailing every week about this stuff? Okay, anyways, okay, so they're tasked to conduct a comprehensive user survey of space weather products. And that is essential to know what the community needs, because it's been a long time since we've developed the products at NOAA and the forecast that we issue. And so knowing what they find out with the survey will then fold it into all of our planning and then all the priorities that I just mentioned with the SWRM. So this is very critical. And so it's not, the ProSwift Act also did, they established the roundtable for innovation exchange among government, among academia, and among the commercial sector. And there's other advisory groups as well out there that are accomplishing how best to become a space weather ready nation. And so a lot of conversation has been circling around, okay, well, how do we all work together to accomplish the one mission, which is, I'll keep saying it, space weather ready nation, right? And so it's a puzzle, right? It's how can we all collaborate and communicate and work together? And we are doing that very well so far. And it's been really incredible to see. And so bottom line, NOAA is committed to ensuring our nation is ready, responsive, and resilient to space weather. NOAA has the Space Weather Prediction Center in Boulder, Colorado, that is the nation's official source of space weather alerts, forecasts, and warning. And then we have the NESDIS arm within NOAA as well that provides those incredible observations needed to issue those forecasts, alerts, and warnings. And Elsa Talat, he is the director of OPA within NESDIS. He has done a phenomenal job standing up the third pillar within NESDIS that is focused on space weather observations that are operational, key. Okay, and so it's not just NOAA, it's just not just NASA, it's all of us working together. It's the entire space weather enterprise working together to achieve this mission and make sure we are prepared for the solar cycle coming up. So now is the time, and we're ensuring that it's done, and thank you.
Let's see. I don't know if my slides can upload it or not. Oh, there it is. Okay. Okay, thank you. Oh. Well, as Jeannie was talking about all this space weather effect, this is one slide basically capture most of the effects. It's really global. It gone from, the solar flare happening at the sun that heat up the upper atmospheres, the radiation effect from the CME transiting, and it affect our comm system, our GPS transmissions. Also, as Nikki was alluded earlier, the heat up the upper thermospheres that, the loss of the stalling spacecraft, and also ground induced currents that affect on our ground system via the power plant. So it's really a global system that affect not just single nations, but the entire human race. So because of that, Nikki was saying earlier, we were chartered by the NASA SMD Heliophysics divisions, Nikki specifically back in 2020, to produce this space weather science and observation gap analysis. So this task was specifically chartered by NASA to look at the NASA observations. So this does not include the ground assets or the NOAA operational observations. But I have a few copies of those if people are interested, but everything is available online. But just to go to, we sort of like what Jeannie was talking earlier, we have a community-wide committee that came up with this report. The whole report is 145 pages, but we look at all the top priority that NASA should be looking at as some of the solar space weather observations are research type observations, and they've been done, like I'm on ACE, and we're actually celebrating 25 years coming up. And SOHO is even older, that provide the only chronograph observations, which NOAA is actively working to get that. But we prioritize a list of observations that we urgently need to fill the gap, and more specifically advance the current forecast and nowcast capability. I can go into that detail, but the first thing is we need, more observations, because this is, like Jeannie said, space is big. And so far we've been fielding a research type of satellite measurements in key strategic point. But when you look at the global system, there are a few things that we identify in the committee where we want to do. For example, if you're looking at the whole Sun-Earth system, we need something not just out at the L1 upstream of the Earth providing key observation, but we also need something off the Sun-Earth line. So when you're looking at CME, it looks a lot better when you're actually looking at the side when the CME is propagating out. And also we look at not just a single point. Right now, we're doing the upstream monitor solar wind with single point measurement. And we already know there are structures within the solar wind. And we were off to that pickup, which is right now driving a lot of, as you'll hear later on, drive a lot of geospace model. And then look at the geospace. The geospace is also large. We have to look at all the IT components and the radiation belt and all that. It's really a global system, but the good thing about what the committee have found is it's all about locations, but we have the current technologies, we have the current measurements. If we put a strategic right measurements at the right place, we can continue and advance our current prediction in space weather. And we actually, like Jeannie was saying, we're looking at the user side and trying to understand specifically what kind of prediction forecast that they need so that we can provide the research and hopefully could be, the ultimate goal of science is you can know enough science to do the predictions. That's the ultimate goal of science. So we can know what the user community wants so we can move in that directions. So I will start with that. Thank you.
Oh, there we go. Hi, everybody. Like Nikki said, my name is Collado-Vega. I'm the director of the Moon to Mars Space Weather Analysis Office. This is a new established office. We actually started in 2020 during the pandemic. So imagine how fun that was, hiring and training people virtually. But we actually have accomplished a lot in the last 2 years. And, I'm going to talk to you a little bit about the office, what we do, our mission, and how we actually had help engage the scientific community into improving space weather predictions. This has been in close collaboration with the Community Coordinated Modeling Center, CCMC, and also the Space Radiation Analysis Group at Johnson. A little bit on the background on why we started. As NASA plans missions beyond the LEO orbit, the low Earth orbit, the need for improvement in space weather modeling capabilities, the communications to the radiation risks to their crew, and also the real-time analysis has deemed essential. SRAG actually serves as the main console operator for the US crew members aboard the ISS. They actually monitor the observations and also use modeling to understand the space radiation environment. As we plan to go to deep space, we actually need novel capabilities. And this actually encompasses beyond the sun-earth line. And this is where the M2M office comes in. Now, a little bit on the mission statement. We were established to support SRAG into the human space exploration activities by providing those novel capabilities of the space radiation analysis. We also support NASA robotic missions, and we do anomaly assessments for the missions. Just recently, we actually helped support the James Webb launch by providing space weather assessments, and we're very proud of that. One of the things that I really want to point out, NOAA SWIPC is and will be still serve as the primary forecasting office for SRAG. We're not here to change that. We're here to actually collaborate and provide that additional support that is needed. Think about it. We're thinking about going to different places, different locations, different events can happen at the same time. And then we're talking about different planetary surface. Our office actually covers the sun 360 degrees, and that's an unique capability that we have. Now, going a little bit more backwards so you can actually understand what happened and how everything got together. The Community Coordinated Modeling Center started a collaboration with SRAG back in 2018. And the idea, the project was actually called Integrated Solar Energetic Proton Alert Warning System. It's a mouthful. And the project actually was to transition scientific community research models that could actually do solar energetic particle predictions for the events, but could be used in real time into and be converted into operations. CCMC did build the SCP scoreboard. You have actually an image there. This is the intensity scoreboard that is actually being shown there. We have 3 of them. We have an all clear, a probability, and then an intensity. Depending on the model, you can get a probability of an event, the time of the start of the event, the peak intensity, or even the profile of the event. So every model is different, every input is different. So CCMC has worked really hard and has done an amazing job to put this tool together. The idea is for this tool to be used operationally by SRAG, and it's actually being used right now by SRAG for the ISS. Another thing that I want to point out, like I said, we cover the sun 360 degrees. So the idea for us is also to collaborate with other missions, for example, MAVEN, which actually we're doing right now, into understanding how we can move forward from the Earth environment and go to, for example, Mars. I mean, we're talking about this space mission here, right? We actually have to think about the future, how we can move forward from the near Earth environment and go to another planetary surface. So we're very proud of starting doing that.
And actually, Yari, I'm going to use my prerogative to jump in on that one because I said I would, which is, also to flag that we have recently taken over operations of the RAD instrument on Curiosity to provide yet more surface knowledge of Mars. Exactly. And we are also, we have the Escapade mission, which is a future mission, which will launch to provide the information about what's upstream of Mars as well as downstream. And so we're looking forward to transitioning all of these science data through you to NOAA to better that prediction.
Yeah, and we're very excited to do so. I mean, this is, thinking about the future. So what does it mean for us to do the real-time analysis? The main thing that you have to think of is for you to believe that a model is actually ready for operations, you have to test it in real time. There's no other way around it. So that's where my team comes in. So you have a coronal mass ejection, for example. And this is one of the examples of one of the latest events that we had, actually January this year. And for people that haven't seen this, my team actually analyzes the CME, the coronal mass ejections, and they actually use different tools and different coronagraphs. Right now we have SOHO and stereo ahead. Unfortunately, stereo ahead is very close to SOHO, so we don't get as much as a view, different angles that we actually will want to. And then we plug it into a simulation. This is the WSA envelope plus cone model. And you can actually see here, for people that haven't seen this before, this is the sun in the middle. This is Earth right here. The planets are circles and the missions are squares. We actually try to support every mission that you see up there. And even we go further down 5.5 AU and we actually support Juno. And the idea is for the missions to know what's going on their direction. So if they have an anomaly, they actually are informed of what is happening. So right here, you can see the CME being ejected. It's actually 2 CMEs in this simulation. My team tries to do everything as fast as possible. Then they put it into the database, which you can see here with all the parameters. We're talking about speed, longitude, latitude, width, and then that actually helps initiate the outputs for the SCP scoreboard. Now, when we try to validate this, this is the intensity. It's being compared to the actual observations of the GO satellite. When we actually do this, we not only validate how the model did, but we also validate how fast we did it, how fast we could actually acquire the data, how fast we actually put it into the database, and how fast the model reacted to that information. Because if you wait a long time, by the time you put this in together, the event is already gone. And we actually have to improve this type of capabilities, and that's what my team does every day. Now, I want to finish, if I can move forward. There we go. I want to finish by introducing my team. I'm very proud of my team. We have accomplished a lot in the last 2 years. We have people from, PhDs, masters, and even undergrads. And believe it or not, the diversity of that team has actually make it really special. Everybody puts something special on the table. And we're so glad to be collaborating with new missions and collaborating with Maven, Solar Orbiter, Parker Solar Probe. And then we're very proud also to start, increasing the collaboration with NOAA, because the idea here is to collaborate as much as possible. And that's the way that we can actually understand and make sure that we have successful future missions for deep space. So thank you so much.
Hello, everyone. I'm Paul Galloway, Teledyne Brown Engineering, Huntsville. Thank you for the opportunity to come and talk today. My discussion today will transition this discussion from large flagship missions and multi-decade programs such as ISS to a new sensor, new technology that can be held in your hand for space weather monitoring. So we obviously have an interest in developing technology for this space weather community, and then getting that technology out as a commercial product. So that's really the kind of the focus of the discussion. Now the fact that the space radiation sensor package that I'm going to talk about today can even be discussed in the same forum with a mission as such as James Webb telescope is amazing to me, and that is brought to that same level. But that just shows you that the importance of the space weather monitoring, the natural environment characterization is to this larger community. And so we're certainly grateful for the opportunity to talk about this new hardware package. So I'm trying to anticipate some questions that may come along in the agenda for the briefing. I'm going to talk about the space radiation sensor package, the background, description of the flight hardware, the capabilities of the system, and the development team and the ownership. Who owns this hardware? What is the genesis for the hardware? And then talk about the technology readiness, maturation status, and our plan to leap the technology and make it useful for this community. And then talk about the availability of the space radiation sensor, the flight hardware, and the data. So I'll wrap it up with that. So a little background on the sensor. It is a new space flight hardware, new technology for space weather monitoring. It's been designed, fabricated, and tested in response to 3 primary initiatives. And 3 of those initiatives are the Secretary of Air Force on space policy, situational awareness, for energetic charged particles, ECP, that came out in 2015. So it's a direct response to that. It's also, there's a specification developed for the hardware by the Aerospace Corporation. That was a direct response to that policy above through the Space Force. And then finally, the NASA, the Heliophysics Division, Space Weather Science Application Initiative, has an objective for expanding the role of NASA in space weather science. Now, I can't say for a fact that NASA SMD had involvement in the development of this sensor. That precedes me, but certainly that reference was called out in the specification. So there was some discussion previously between the U.S. Air Force and NASA with regard to the sensor. And finally, the last thing there is the Air Force contracted with Teledyne Brown to produce the space weather sensors. And that's what you're going to see today is kind of the result of that contract in the current contract that's ongoing. So a couple charts on the flight system description. It consists of an energetic charged particle light, ECP light is what the Air Force calls it, sensor with a suite of radiation, plasma, UV light, and static electricity detectors. It's been developed and qualified for space radiation, vacuum, and temperature extremes. It's not a PowerPoint briefing. It's real hardware that exists and is currently being tested and developed and ready for distribution. So it's been optimized for space weather detection on multiple platforms. You'll see that as I show the pictures, which was really good forethought on the part of the Space Force. They want to be able to get this system out there and get it distributed so they can have nodes that they can rely on for the data. And as well, this community can rely on those sensors and for the data as well. So it does provide the ability to determine, to analyze and determine the natural environment and the induced environment, possibly hostile events. So the Space Force has a different charter than NASA. Their charter is not science, as you know. So their goal, I think, haven't talked with them, they haven't told me, but I think their goal is to distribute this sensor out and develop a node or a set of networks with this data. And then they can establish the baseline with their measurements with the sensor. And then should there be a hostile event, then they can look at the increase above the baseline to determine if there has been something that occurred out there that's of interest to the Space Force and the military community. So I believe that's their goal, haven't told me directly. It does have a small footprint. It's a bolt-on, it's low mass and low power, which makes it all benefits to placing in multiple locations, whether that be a launch vehicle as a secondary payload, whether that be as a part of an instrument suite. So it's modular, it can be placed in a lot of locations. As you'll see, I have more descriptions on that. So a little bit more on the details. Mass, 6.6 pounds, power, 3.3 watts. Dimensions, you can see quite small. The command and telemetry interface is RS-422, which allows it to plug into a lot of different systems. And then it's been thermal vacuum qualification tested for non-operational temperature range -35 to +70, operational -20 to +50. So as you can see, it's quite small, low power, and has a simple mechanical interface that I could talk a little bit more about later. So this makes it suitable for wide distribution among sensor suites and launch vehicles. So there's a picture of the actual flight hardware on the left. And now we'll talk about transition to the capabilities of the system a little bit. You can see the suite of sensors there that are called out in acronyms. I'm going to talk a little bit more specifically about all those sensors. Not going to take a lot of time doing that. But you can see it also as a bolt-on has a very simple mechanical interface. But that simple interface causes issues. So if we want to, it's not robotically compatible. So I'm going to talk a little bit later on a future experiment for space station, how we would actually make this robotically compatible to get it from space station inside to the unpressurized volume. So that's one limitation, not robotically compatible. It really would need to be bolted on pre-launch into your sensor suite or launch vehicle. But we do have an idea for making it robotically compatible as a better interface for ISS external payload. So this table really just defines all of those sensor packages on there. There's there's 6 dosimeters on there, low energy transfer micro dosimeters, low level, 4 medium level, and 1 high level dosimeter. It has a 2 UV photodiodes. It has a surface dosimeter, a discharge device for electrostatic discharge recording. It also has a charge and discharge sensor. And then the final 2 items on there show the interface to the launch vehicle or host vehicle. It has a power connector. It requires 28-volt interface, which is common on most vehicles. And then the 15-pin RS-422 connector. It also has some analogs that go through that connection as well. And now, not shown on here, there's obviously other things. There's a rad-hardened FPGA as part of the system. There's power conversion from 28 volt down to lower voltages to operate these sensors. So not everything's listed. That's really just more of the sensors I think that might be of interest to this community and the capabilities of the system for space weather detection and natural environment characterization. So who owns this sensor? Who's the development team and the ownership? So this is a perfect example of the from our policy discussion the other day of a private-public partnership. This one is. You have 4 organizations involved with this from the beginning to where it is now, and it's primarily the Air Force is working the contracting side of this. The U.S. Space Force did the hardware development funding, the technical oversight, and the data utilization. So Space Force is the owner of the existing flight units. The Aerospace Corporation did the engineering and qualification testing for the unit. They're the owner of the design. So they've tasked Teledyne to come out and to not only, we supplied most of the sensors on the system, and we also did the integrated system manufacturing. So we've been tasked for commercial marketing and distribution based on approval from the Space Force and the Aerospace Corporation. So we all work as a team. So I appreciate the question asked earlier about where are the uniforms? Well, I'm not wearing the uniform, but I'm representing the uniforms with this product. So they see that NASA community has a need for this sensor. They want to make it available, and then they're using Teledyne to make it available. So what is our plan for maturing the TRL of this system? It is a brand new system. It hasn't flown yet. So our near-term goal is to increase the TRL from 4 to 9, and we're going to do that using government and commercial flight opportunities. So there is planning to launch an ECP Light or SRS on the NASA Artemis lunar mission, but that launch is a few years away. I mean, we don't really want to wait 2-3 years to mature the TRL from 4 to 9. So we internally at Teledyne are looking at other opportunities to do this. So one of those opportunities, it wouldn't be right to not talk about a space station experiment as part of this forum this week. So we are looking at an opportunity to place the SRS package on the ISS via accommodations on our commercial facility, the multiple user system for Earth sensing. So it's a precision pointing system or gimbal system. And our facility has been operating continuously on ISS since 2017. We're coming on our 5-year anniversary of continuous operations. So the SRS would provide space weather characterization for the ISS environment if we're successful in developing an external payload for space station. And we're working toward that goal, as you'll see in the upcoming chart. So we got a few images on the MUSES system. The left is a pre-launch image of the MUSES platform that was developed at Teledyne. And then we did it as a commercial venture to provide a pointing platform for Earth observation instruments. And that lower image there is, upper image is MUSES in the launch configuration with no instruments. And then the lower image is a fully outfitted MUSES with 4 instruments. So our company has been successful in flying a hyperspectral imager. That's it in the middle there. That's the DESIS hyperspectral imager that was installed in 2018 on the MUSES system. So we gather that data, and then that data is distributed to commercial users and government users across the world. So we have 3 other slots available on this MUSES system. So on the right there, you have a view of the Muse's large hosted payload that's during assembly. So you get a kind of the scale of a large Muse's payload. So our goal is to build a new Muse's payload, install the SRS in that payload. So that would give us the capability to make the SRS robotically compatible. We can't take SRS directly from the pressurized volume to the external volume based on its current design. So we have to make it robotically compatible, and the Muse's large hosted payload would give us that opportunity to make it robotically compatible for ISS. But you can see there's plenty of volume in that large payload for not only SRS, but other equipment as well. So what about the availability of the space radiation sensor? So this is my final chart. Discussions are invited for the following areas. We would be interested in talking to potential users about building copies of the SRS for both government and commercial customers. So we invite those discussions. My email address will be on the next chart. We also are looking at flight opportunities for SRS as a secondary payload on government or commercial missions. So we as owner partner in that system, if you have a launch vehicle, if you have an instrument suite that you think this sensor would be useful for, we would like to talk to you about adding that sensor to your system. And then you would have access to the data. We would have access to the data. So it would be a win-win in that case. So it's not where you purchase the unit, but you make your vehicle or suite available for the sensor based on the technical performance that I showed earlier. And then finally, because we're looking hard at developing a second Muse's payload, Muse's is an ideal platform for Earth observation hardware from ISS. It provides direct exposure to space vacuum and space radiation. It's low cost and access to space for imaging equipment, environmental sensors. So what we would do is, in that case, is, as I just talked about earlier, we would fly SRS in that same canister with another Earth observation instrument. So if you have an Earth observation instrument or any other hardware that needs access to space vacuum or space radiation, we could partner with you and put your hardware in that same canister and launch it through the ISS commercial cargo program, get it moved from the pressurized compartment to vacuum and installed on Muses, and you could have direct access to space for the life of space station. So that concludes my discussion
Right,
on space
thank you.
SRS.
Thanks, Paul. So now I've got a couple of questions before we throw it out. So as Paul alluded to in his presentation in the Heliophysics division, as part of our Space Weather Space Science Applications program, we have been sponsoring pipeline instruments, and this one is actually one of the ones that we've been sponsoring. So, I'm curious, with that in mind, to ask the panel what kind of instruments, and the reason that we're doing the pipeline, by the way, is to be able to take advantage of quick turnaround hosted payload opportunities. And so a couple of years ago, we were given the opportunity to put a space weather package on the first module of the Lunar Gateway. And at the time, we actually had to deliver it in less than 2 years. And so there was not much time to do anything other than say, what do you have lying around in the lab? And can we put it together and make it into a space weather package? But we realized then that we really wanted to be ready and actually have things kind of in the pipeline or in the pantry. Everybody jokes, I need to have a little space weather pantry that I can open and take out an instrument, pop it on something. So I'm curious as to what kind of measurements the panel thinks would be sort of the most important that maybe we should be focusing on. Go ahead. Yeah. Any order.
Okay. So I'm actually really excited to see his presentation here, because to know what's going on with the radiation environment has been critical for NOAA, because we've been tasked to provide modeling and alerts and warnings for the radiation environment for our aviation community. And so that is one of the measurements that's missing largely. And so we've been hesitant to do that, but we have an international mandate with the International Civil Aviation Organization, which is a UN body The Space Weather Prediction Center is one of the 4 global providers of aviation alerts and warnings. And so knowing that radiation environment is huge. And so I'm really excited to see his presentation on how we're advancing that. So that would be my number 1 suggestion.
Well, Nikki, you know I'm biased. I absolutely agree. I mean, I build energetic particle detectors. I flew all the way from Mercury to Pluto, so I'm a little biased on that area. But to respond directly to your questions about, pantry of interest, I think it's a good idea. We actually, APL has been approached by a couple of sponsors just recently within a month or two, trying to take advantage of this launch capability. It's still being worked, but in order to actually, because right now we don't have, the pantry is empty because of all sort of, right now when we got sponsored to build an instrument, that's the only articles we have. We don't have a flight spare. We used to have flight spare, but we flew all that. The only thing we have is an engineering unit lying around. Time to refurbish that, you're dealing with plastic part, either the FPGA is a silane versus the L and stuff like that. And also now we're coming up with the supply chain issue. It takes I heard it takes like 18 months to get a high voltage capacitors order, or not even the FPGA. So I think it's a great idea, but realistically, I think it will take still at least a couple years for, even if you have something lying around, to refurbish that. And it's gonna take a little bit of money to get that involved, to order the parts and all that. Even if you have a design, it just, with the today's situation, so as I was saying earlier, we got approached by a couple of sponsor, and they want us to fly something by the end of the year, and it's just hard to do.
Put my space weather analyst hat. And there's a lot of limitations right now as we do real-time analysis, to be honest. For example, we definitely need something at L4. We are having, for example, just recently, events that happen above the west limb of the sun, like looking directly from the earth. And we receive those energetic particles and we cannot see the source because we don't have anything on that side. Not only that, I always receive messages from the Meehan team like, Jerry, what's going on? We're getting signatures of stuff and we don't know exactly what's going on. I was like, well, I cannot help you too much on that because we cannot see the far side of the sun right now. So there's a lot of limitation in terms of us protecting the assets. We have missions across the whole solar system. And for us to determine the direction of a CME, we need to understand the source. And if we cannot see it, then we're just doing a guess approximation. And that's not good enough if we want to send astronauts to Mars. Not only that, we need solar wind monitors, beyond the sun earth line. For example, Mars L1, that would be a great idea, because that way, if you have astronauts on the planet, they don't have to depend on Earth, right? And they actually cannot depend on Earth. There's going to be a huge amount of time that they're not even going to be able to communicate to Earth. So they need to have that kind of capability on the planet. Another thing, we do a lot of anomaly assessments for missions, and sometimes they ask us, like, does the space weather have anything to do with this? And we're like, well, probably, but because they don't have particle detectors, particle measurements, we have no clue if it's actually true or not. So sending missions out with some type of particle detector, that will be amazing because it actually will help us understand the environment they're in and how space weather affects them. So those are 3 of many that I have.
Well, I'm not a space weather scientist, so the aerospace defined the requirements, we executed on those requirements and built the system. But I can just tell you on the affordability of the system, Space Force has already taken all the risk out of this system by building it. They've designed it, developed it, qualified it for the environment. So for a commercial company like us, they've reduced that risk down to now we just have to price another unit that we've already built. So that's certainly very attractive to us as a company. But we could take requirements from scientists, convert that into a system that would operate in pretty much any environment, whether that be a launch vehicle, an instrument suite. So I'm not sure I have the answer to your question, but that's our perspective on that.
Great. I really appreciate that. I'm looking at the time. I think we should probably go to the audience because we're almost out of time. So if anyone has a question, please raise your hand.
Okay, we're getting microphones and let's get one to over here real fast. Y'all have to give up a couple of right over there. We have one from online, I think.
What are some of the emerging technologies in space weather instruments, and do you see a quantum tech having a lot of potential in the field?
I'll take a crack. So as you heard, probably we talk about the space is large and we only have point measurements right now. I think some of the emerging like heliospheric imager, for example, that look at the whole solar wind propagations by just doing remote sensing, that provides a lot of capability because you just can't populate the whole space with in situ measurements. So I think looking at some of the remote sensing imaging instrument would be good. Also trying to, one of the sort of holy grail in the science is trying to get the interplanetary magnetic field, the component northward versus southward, and you can do actually prediction as the CME propagate, because the Earth dipole is oriented in such a way, and the northward and southward IMF make a huge difference to drive the, so those are the two areas I'll be looking at. I don't know if others have.
So there's a lot of other capabilities being developed right now. For example, there's a machine learning conference going on right now in Colorado, and it's machine learning on heliophysics. And the idea is to actually implement machine learning capabilities into predicting space weather, but it's not a simple thing. You know, there's a lot of things that go into consideration. Well, I actually was part of a project that we try to detect the CMEs automatically, and not only detect, but measure them. And it was very, very difficult. It's a project that is on hold. But you know, eventually the idea was to make it more robust, more automatic for us to actually just put those measurements into the simulation as fast as possible, and then make sure that the models get that input and they can actually predict the forecast. There's some models that work only with observations, but there's a lot, the very developed physics-based models, they actually get triggered by either the CME parameters or the simulation. So that's really important for us to improve moving on to the future.
Okay, I'm going to ask one because this is a thing that's probably obvious to the casual observer other than me. But we've talked a couple of times about losing control or having a problem with 40 satellites all at one time. We even had a little video on it, but what happened? Did we not know it was coming? Did we not care that it was coming? Did we not recognize that it was going to have an effect? I come from an environment where stuff like that happens and you put in processes for future so you don't have that happen again. So what happened and what processes are we putting in place?
All right, I'll kick it off, then I'm going to pass it to Ginny and Jari to answer. But I mean, we certainly knew the event was coming. We saw the event come from the sun. We tracked the event. The thing is, it was a very moderate event, and if in depth. So we also have measurement gaps, as George just alluded to. This is a giant space that we have to predict. And I've often heard my colleagues at NOAA use terms like, well, it's trying to say what the weather would be like in California from a weather station in Africa. It's hard to do that. Right now, we do have a measurement gap in a critical region. And there is a future NASA mission called Geospace Dynamics Constellation, which will be 6 spacecraft that will actually orbit through the very region and give the information about that drag, because it really was that the whole atmosphere heated up and expanded. And so the SpaceLink spacecraft themselves have electric propulsion, which is great, absolutely fabulous, except it couldn't sort of overcome what the environment was throwing at it. And so they were unable to actually just raise out of this problem. And so they re-entered. Had we had Geospace Dynamics Constellation giving us real-time data, we would have now casted that problem was going to happen. That said, we did know that the storm was coming, and we probably would have predicted it was not a good time to actually launch. Jari, you want to jump in? Grab the mic off Paul. And then.
Yeah, as a NASA person, we did know that the CMEs, there were 2 of them, were coming. By the time that the launch happened, one of them actually had arrived. But if it was a very interesting event where you had the shock, be very separated from what we call the flux probe, which is the magnetic cloud of the coronal mass ejection. However, that magnetic cloud had a significant IMFBC negative, which is what George was talking about. And because of that, it created a geomagnetic storm. That storm went down a little bit, and then it went back up because another coronal mass ejection arrived. Those 2 coronal mass ejections were not too significant, but having that kind of activity, you know that you have geomagnetic disturbances happening. So at that point, I would have said, no, that's not a good idea to launch on that perigee, because it will definitely be affected by the heating, like Nikki said, and the density increase in that part of the ionosphere. So, I mean, we just need to work with everybody, collaborate with everybody, so this doesn't happen again. And in terms of NASA, we're definitely interested in developing those models that could actually help us understand that type of environment. Right now, we can definitely create different scenarios of what would happen if you get this type of CME, this type of geomagnetic storm, and how that would affect the ionosphere. So we're moving forward on that collaboration.
Yeah, and I just want to say something from the NOAA perspective. I applaud SpaceX for being so transparent about what happened, because understanding the user needs and how we could better predict and forecast and observe what they need and make tailored products for those uses is incredibly important. And so we reached out to the SpaceX team as soon as they posted that news article, and we wanted to understand, NOAA did, and I know NASA has as well, about what exactly happened and how we could have helped, and also to educate them on, okay, here's the products that we have, because at NOAA we have an operational model called the whole atmosphere model. And what we do is online, you could see it 400 kilometers. Unfortunately, that didn't quite work because they launched at 210. Yeah, so what we did was like, well, we could actually expand that to 3D. And so we've been able to pull that data, see it at the 210, and we saw those anomalies and those structures that SpaceX did not plan for. We didn't even know how structured that would be. And so that's a model and application that they could have used. But we did all know NOAA did issue those alerts and warnings for that storm perfectly. And so they knew and they saw, they just didn't appreciate those lingering effects and those structures that would happen in that very low orbit regimen. So yeah, I applaud SpaceX, and it's been incredible working with that team and with NASA to understand exactly what happened. So yeah.
Thank you.
I actually just really want to echo what you said, that SpaceX reached out immediately, and we've had many meetings with NASA and NOAA in partnership about, how can we use our data that we have right now? How can we transition it? How can we help improve the WAM model? And we're actually really looking forward to it, and giving the predictions moving forward. SpaceX immediately took a mitigation, which was they're going to launch to a higher perihelion for the short term. That's not so good for SpaceX because they can't launch as many, but at least they'll be out of this sort of danger region. But yeah, it was wonderful to work with them. They were immediately transparent about what happened. Yeah.
Great. Thank you for that explanation. I even understood it. It's amazing. I'm getting educated in these places. It's so surprising. Anybody else? One more, last question, back in the back.
A question for Paul. I noticed that you mentioned you were going to use the ECP light on the Artemis mission. How do you intend to do that? If it's on the moon and has to deal with the temperature range, as I noticed you had like a set temperature range that it would be best operable.
That's a good question. Obviously, we have to analyze for that environment. It's qualified for the environment you saw. If the analysis shows that we need a wider range, then we would go back and requalify for the wider range. But also, you would use active heaters to get the system within the range. Also use MLI and coatings to keep the temperatures extremes lower. So it's a matter of a full thermal control system in lunar orbit. So but it could be a problem. We just got to look at the environment. I have a chance to address, there's been a lot of discussion of gaps. I want to talk really a gap in the technology development for space weather detection, test bed availability. On ISS, I've worked on over 40 payloads now, not all ISS, but the cost of access to space vacuum, space exposure is really an impediment to a lot of technology development. I can, working with CASIS, NASA, I can develop a pressurized payload on the order of $1 to $2 million for a short-term experiment. But when you move from pressurized to unpressurized, the cost goes up by a factor of 5 to 10. And that's an impediment for startup companies. It's an impediment for universities that could be doing research in this area. So the reasons for those cost increases are robotic compatibility, getting it installed on ISS. The other is rad-hardened, rad-tolerant electronics are quite expensive, and that drives you. Those can be multi-million dollars for one processor. And then just the environmental testing that was mentioned earlier, that's quite expensive. So there is an impediment for test bed work in space vacuum, in space radiation environments. Just wanted to bring that up. If anyone want to look at basically closing that gap and looking at funding for experiments that are space weather related to applications on ISS.
Great, thank you. So I'll
Really?
close the panel. Is that
We're
right?
done with the panel.
We're done with the
We're
panel?
done with the conference,
right.
except my script says we will transition to lunch. So we will transition to lunch. Nikki, thank you very much. This has been a lot more informative than I thought it was going to be.
I'm not sure how to take that.
No, maybe that's because you put it in a way that I could understand it.
Thank
An
you so
engineer
much.
could understand. So we thank you all for this. We thank you, Nikki, for the panel. We